All right, so we're going to go through, we're starting with the conjecture booklet question 6. Okay, so we've got the function x to the power of 3 on top of x plus 1, where x does not equal minus 1. All right, because it's not going to make the denominator equal 0. Sketch the graph, clearly showing the axes intercepts and the vertical asymptote. So I'm going to hop on a Desmos, bring it up. You guys pull your calculators out, bring it up. And we've got, and I'll just do a rough sketch of it, x to the power of 3 on top of x plus 1 looks like this. Asymptote there, like this, flat up, and then here. Local min. All right, so just a rough sketch. We'll skip over that part, on to the next part. Okay, the graph has 2 stationary points. One of these stationary points is at 0, 0. Find the x coordinate of the other stationary point. So it's saying, what's the x coordinate of this local minimum here? So we'll just g solve min, and I've got minus 1.5. Okay, now consider the family of functions x to the n on x plus 1, where n is a positive integer such that it's greater than 2. For all possible values of n, g of x has 2 stationary points. One of these stationary points is at 0, 0. The other stationary point is at a. All right, so this is point A. All of these kinds of functions are going to have this kind of shape. And we're interested in the x coordinate of point A. So it says fill in the table in the form A on B. So we have n, the function is x to the n on x plus 1, and we have x coordinate of A. And we're told the first one. All right, now in our first circumstance, we investigated 3. All right, we saw 3 was minus 1.5. Now, if you can't see what that is as a fraction, you can type that in your calculator and press the S to D button or the F to D button, fraction to decimal button, and vice versa. So that'll convert it to minus 3 on 2. All right, you can see 3 divided by 2, 1.5. And maybe you can already start to see a pattern, but let's check for n is 4 and n is 5. So you put it in your calculator, we're going to have x to the 4 on top of x plus 1. And it becomes a local max. When I have an even number, it's down here, it's a local max. And the x value I've got is minus 1.33. All right, so that's 1 and a third, 1 and a third, minus 4 on 3. And we'll go to x to the 5 on x plus 1, and we've got minus 1.25. So that's 1 1/4 or 5 on 4. All right, and so we can see this number's going up by 1. So this number's n, and at the bottom we have n take 1. All right. So on the basis of your answers to part B, make a conjecture about the x coordinate of point A. So, x coordinate of A. If it helps, what you can do is add on another row here where you've got n. Okay, we've gone 2, 3, 4, 5. So that means n is going to be at the top. We have this negative out the front, and at the bottom, each number is 1 less than n. So we can put n take 1 at the bottom. So our conjecture, the x coordinate of A is going to be minus n on top of n take 1. All right, and then prove our conjecture. So to prove this conjecture, it's a stationary point. We know stationary points occur when the first derivative is 0. So we're going to take this function here and we're going to differentiate it and make it equal to 0 to find its stationary points. So I'll try and work here. Hopefully there's enough room. We've got the function x to the power of n on top of x plus 1, and we want to differentiate it. All right. So you can anticipate, right? Even if you're doing tangents, whether I said it's either going to be a tangent or a stationary point, you just have to differentiate this function. You're going to get some marks there for doing that. So that's going to be your first step always. Here we're looking at that. We've got u on top of v. We have to use the quotient rule. And the derivative of x to the n is just nx to the n take 1. U dash v take away uv dash on top of v squared so in order to communicate our answer, right, I'm just doing maths here and I suppose I'm communicating it to you verbally, but to make sure we're communicating it clearly, we should say something like stationary point occurs, maybe even here, stationary point when f dash of x equals 0. All right, so we're saying stationary point when f dash of x equals 0, here's f dash of x, we're finding when it's equal to 0. Because it's a rational function, we can just completely disregard the denominator and we're only interested in the numerator. All right, so then looking along there, if we're going to solve something like this, we want to factorize, right? We're going to factorize. And I'll show you how should we do this. I'm looking now, I'm thinking x to the n is common there. And here what we have is we've got, yeah, let's express this like this. All right, yeah, that's going to factorize out nicely now. So if we look along at what's multiplying here, all I've done is rewritten this like this, right? X to the n take 1 can be expressed as x to the n on top of x to the 1. Okay? Because if we're doing index laws, it's the top power take away the bottom power. That's what it would simplify to. And now you can see we've got x to the n in this term. This is all one term because it's all multiplying, and we have x to the n is common. So we're going to pull x to the n out the front, and we're left with n on top of x all right, so that's where the tricky algebra is coming in, right? Any questions about that? All right, so then we'll keep going. Applying the null factor law, we have this solution, x to the n is 0, and here we can just sort of expand this and solve this. We've got n on x times x, so I'm going to call that nx on x, plus n on x, take 1, equals 0. Now here, so the solution here is x is 0. And remember they said there's always a stationary point at 0. We saw that in all the graphs. This one, right? The slope is horizontal at that point. So we expect that to be one of our solutions for this family of functions. We're more interested in what's going on here. So what I've done, I've just distributed it there and there. X at the top, x at the bottom, that'll cancel. And so we've got n plus n on x take 1 equals 0. And we're trying to solve this for x, right? We're trying to solve this for x. So what we'll do, let's multiply both sides by x. That's going to allow us to get rid of the denominator, right? And so then what we're going to have is we're going to have nx plus n take x All right. And how are we going to crack this? We've got n. So this is me. I don't have any solutions here. I'm just fumbling my way through it. This is how you're going to be doing it in an exam, right? Just keep wrestling with it. Keep trying to break it down. So, like if I look at these two terms, I can factorize n. So we've got n times x plus 1. Take x. All right, that's not particularly helpful. I know what we need to do. We're trying to get x by itself, right? Okay, that's a hint. We're trying to get x by itself. So let's disregard that step. Now, when you want to cross something out in your test or your exam, you just need to put a line through it, okay? And then you say, look, let's go over here. All right, we want to get x by itself. So I'm just going to rewrite what we've got here with the x's next to each other. So we're going to have nx take x plus n. Okay, now we can factorize x. And what that's going to do is give us one lot of x, right? If I factorize x here, I'm going to be left with n take 1 plus n. All right, and now you can see the solution. Move n across, divide by n take 1. I'll do that in a sec. I'll get these lights. All right, so move the n across and then divide both sides by n take 1. Beautiful. QED. All right, so you can see, they're not easy problems. Let's just recap. How did we prove this conjecture? Well, it's a stationary point. We know that stationary points occur when the first derivative is 0. We find the first derivative, it's a rational function, which means we just disregard the denominator. It's going to equal 0 when the numerator is 0. And we're always trying to factorize so that we can apply the null factor law. So we successfully factorize. We expect this solution. This is the first stationary point. And then in here, I'm trying to isolate x by itself, right? I'm trying to get x by itself. So sort of expanded that. And here, it's like just breaking it down. Just keep hacking away at it. And you saw, I'm thinking, all right, I need to get x by itself. Factorizing n's not helpful. But factorizing x, what the beauty of that is it reduces this term. You see how we've got x here and x here? If I factorize x, it gives me one lot of x, okay? And we want x by itself, so we're trying to isolate x. So that's why we took that path. All right, so we'll do the next one. All right, you guys have a quick start. I'm just gonna get a razor to clear the board. This is one here. All right, anything to ask about along that one, or?
You got any tips to do those, like, if you don't know how to do them?
Like when you get to here?
Yeah.
No, just keep hacking. No, seriously, just keep hacking. Like you saw me, I'm thinking, oh crap, I'm doing a performance in front of you guys here. How do we do this? And admittedly, I'm a teacher, but still, exposure to them. It's going to be one you've seen if you've done all of them, right? So
like 20 of them.
You just remember all of them.
Yeah, or
put them on your cheat sheet.
Put all of them on your cheat sheet. Yeah. All right. This is not the one from the exam last year, but this is still a good one. Okay. Figure 9 shows the graph of x ln of x squared plus 2. And the tangent at x is 1 is there. Okay, show that dy on dx is this. So we need to differentiate. If we're going to differentiate this function, we have to use the product rule. We've got u and we've got v. So u is x, u dash is 1, v is ln of x squared plus 2, and v dash is going to be 2x plus 2, 2x on top of x squared plus 2. And then product rule u dash v plus uv dash. Alright, which is what they've got there. They've joined the x and the x squared together. Okay, hence show that the tangent at x is 1 has this equation. So for a tangent we need two things. Who can remember what they are?
Point of contact.
Point of contact, very good. And
Slope.
slope, nice. Okay, so the point of contact is x is 1. So when x is 1, we go, what's the y value? We put that number in here. It's going to be 1 times ln of 1 plus 2. It's 1 ln 3. All right. If it helps, write that out. F of 1 is 1 ln 1 plus 2. That's 1 ln of 3. ln 3. Okay. For the slope, we can see it's going to be ln 3 plus, I might write this one out, f dash of 1 is going to be ln 3 plus 1 times 2 on top of 3. ln 3 plus 2/3.
What did you get the 2/3?
That component. Because when we put the number 1 into the slope, f dash of 1, ln of 3 plus
okay.
1 times, yeah.
Yeah.
Excellent. So then if we smash all that together, they've got it in y-intercept form, so we're going to do that too. So the equation of a tangent is y equals mx plus c. I'm just thinking, yeah, we'll just do it this way. Y equals mx plus c. We've got m is ln of 3 plus 2/3 times x. And we go, when x is 1, y is ln 3. So we put ln 3 where the y is. Can you guys see this? Alright, so when x is 1, y is ln 3. I've put ln 3 where the y is. I've put the number 1 where the x is. We've got ln 3 on both sides, that can cancel. And because it's multiplied by 1, and so we've got c equals minus 2/3. So therefore the tangent is take 2 and 3. Good. Okay, part 3, determine the y-intercept. Y-intercept when x is 0. 2/3. Okay, all okay so far? Yep. So, like some of those marks can be tricky to get right, but we want to make sure we're getting these ones. All right, I'll clear a bit of space here, I think. So, next part said, consider the family of functions x ln of x to the n. So again, we're changing that value of n. And they've even filled the table in for us. Look at that, beautiful. Fantastic. Okay, so I'm going to fill that table in. 3, 4, 5, x ln x to the 3, x ln x to the 4, x ln x to the 5. 3 plus 3, and here we've got minus 3 on 4, minus 4 on 5, minus 5 on 6. Make a conjecture about x ln x to the n plus n. Okay, what do we notice about this n and this number here? They're the same. 4, 4, 3, 3. So we're going to say minus n on top of, and this one's 1 larger, isn't it? Minus n on top of n plus 1. So the conjecture, like you have to answer it in the context of the problem, y-intercept equals minus n on n plus 1. Very good. Okay, let's get on to the proof of this one. Do you guys want to have a try first? You sure?
Sure.
So, yeah, have a try. So, I'll pause for a sec. So you're doing a tangent. All right, we're finding the equation of a tangent to this function. So that means you need the point of contact and the slope. So here's the function. You've got x is 1. The y value is going to be 1 to the n plus n. All right. ln of 1 to the n plus n. And you need the slope. Okay, so you can differentiate that using a pretty similar process to what we did over here. So you get the point of contact, get the slope. At least do that. Get those marks there.
What's the point of contact?
We're talking about when x is 1.
Okay.
Yep. So yeah, you're finding the tangent at x is 1, and you want to prove that the y-intercept is this. So we have to find the tangent.
Mr. Royal,
Yes.
when you did the point of contact with y, why does the n go away there? Like
There.
no, up like where you were just now. No. Yeah.
Oh, very good.
The
So
point of
1, so we're told n is a positive integer. 1 to the power of 2, 3, 1,000, doesn't matter, always equals 1.
Okay.
Yeah, good. Yep, good question. Yep. Yeah, and I was going to say that in a sec, but all done now. Too small.
A little bit. My eyesight's like I can't read anything.
Oh, I actually got it.
Well done. Yep, see, keep hacking at it. So now,
Attention, Zali Golubiowski, can you please go to Mum's car? Thank you.
you're just looking to find a tangent with those properties. and show that the y-intercept is what we predicted. Well, I'm going to pause the video camera and just float. So I'm just going to offer an explanation up to this point. So if you're happy, keep doing what you're doing. If you want to have a look, have a look. So we've got the function here, and we need to find the tangent at x is 1. That's what we're trying to do to prove the y-intercept is what we predicted. So for a tangent, we need two things, the point of contact and the slope. In order to find the point of contact, we've got x is 1, and we're putting that number back into the original function. So you can see we have 1 ln, 1 to the n, plus n. Now 1 to the n, 1 to the power of any number is just going to be 1. So it simplifies to ln of 1 plus n. That's our y value, that for the point of contact. So we've got the point of contact. Next we need the slope. And so in order to answer the slope, we need the slope function. So we need to differentiate this one. Again, it's the product rule. We've got u times v. So u dash, v dash. Smash all that together. And I'll just talk about what's going on here. Here I have x times nx to the power of n take 1. And x times x to the n take 1 is equal to x to the n. So they collect together. You can use index laws to bring them together, right? It's like this, x to the 1 times x to the n take 1. Well, they have the same base, so we can add the powers together. N take 1 plus 1, x to the n. So that's what's going on there. Bring them together, and then we're putting the number 1 in, because we want to know the slope when x is 1. So I put 1 there, and I'll put a 1 there, and I'll put a 1 there. And 1 to the power of n, we've said is just 1. So that's what that simplifies to. We've got the slope, and now you need to bring all of that together. You're probably at 4 marks out of 6 so far, or 3 out of 5 or something. Bring all that together to get the y-intercept. All right, so a tangent, that's its slope, that's its point of contact. So start y equals mx plus c, put your m in, and then put the point of contact in to solve for c. That's what you're trying to show. Finish it off. All right, so we've got y equals mx plus c. So this is our m, this is our slope. So we'll have y equals ln of 1 plus n, plus n on 1 plus n. It's a big, massive thing, isn't it? But that's mx plus c. Okay, I'll draw a line here to separate
I had to
them.
like rewrite it a million times because it's so long.
It is so long, isn't it? But just keep it in brackets, treat it as one thing. And now we're putting in the point of contact. We've got when x is 1, y is ln of 1 plus n. So I'm going to put 1 plus n where the y is, ln of 1 plus n. And I'm going to put 1 where the x is. So because I'm putting 1 there, it's multiplying it by 1. This is just what it's going to become, right? ln of 1 plus n on 1 plus n. We've got one lot of it, and then we've got this plus c hanging out over here. Now we're trying to get c by itself. We've got ln of 1 plus n on both sides, so we can eliminate that component. And now we'll subtract this from both sides, or we're just moving that over here. We're going to have minus n on 1 plus n equals c. C is the y-intercept of the tangent. So where was our conjecture here? QED.
So I didn't actually have to put it back through.
No, you don't need to. You can make the statement if you want, but y equals mx plus c. M is the slope, c is the y-intercept. Here's the y-intercept. So yeah. Yep. Excellent. All right. So 8. I reckon we can do one more. Yeah. Excellent. You guys want to have a crack again yourself?
Yeah.
Yep. I'll pause and have a read.